Hello everyone, welcome back. Let's firstly also review what we have talked about before. So in the last lecture, we have talked about the underfitting and overfitting, and we have used these simple examples to demonstrate what is underfitting and what is overfitting. We said that underfitting means that our model is too simple and it has very high tuning error, and it also has very high testing error. On the contrary, for the overfitting, so overfitting means our tuning error is very low, but our testing error is very high. So we said that in real practice, we don't want underfitting, and we also don't want overfitting. But sometimes overfitting will occur. So in this lecture, we will mainly talk about how to prevent overfitting. Mainly in linear regression. So this is the topic we will mainly cover today. Okay. The first solution for this problem is that we can see that the overfitting occurred because we have very limited data. So if we have smaller data, the overfitting is more likely to happen. On the contrary, if we have more data, means that our model will be harder to overfit our training sample. Thus, the first solution to prevent overfitting is that to have more data. And this is a easy or very hard solution. Sometimes we are unable to get more data. Maybe because our tests needs funds, so we cannot have more data, or the data in your area is very limited. There's no way you can find more data. Okay, so the next solution is that you can use regularized linear regression. And this will be our main topic today. Okay, as usual, I will also start with examples, because I think examples will make you understand the concepts better. So let's also start with the example we are keeping using. So suppose we want to predict the price of the house. So I think after you have watched these videos, you will all be very familiar with purchasing some houses. You will be an expert on this. So if we want to predict the price of the house by the area of this house, so the feature would be the area, and the output would be the price. Let's assume we have a very limited training data. Let's assume that we only have 2 houses as our training data. This is a very limited data. Training data, we only have 2 samples. If we only have 2 samples, if we use linear regression, if we use the linear model, we know that 2 points can decide a straight line. So this is more likely the overfitting will occur. if you ask the optimization algorithm to find the minimum residual sum of squares, it may give you a straight line like this. I will name this one, this straight line, model 1. This is the model 1 you found. Maybe it's something like this. Y hat, our prediction equals to 20 plus 2x. So this is the slope, and this is the intercept, the bias term or the bias term. And this is the training data. Of course, we have some testing data. Suppose our testing data is something like this. This is our testing data. And you will find that this one, the model 1, is an overfitted model. So when you apply it on the testing data, when you calculate the error on the testing data, you will have a very large testing error here. You calculate the distance, this distance, and take the square, and you make a summation. You will find that the testing error is very high. So let's write something here. Let's draw some of our conclusion here on the model 1. Model 1, we know this is a overfitting model. Overfitting. And you can see the residual sum of squares on the testing data is equal to nearly 0 here. Because we only have 2 training samples, and this model can predict these 2 training samples perfectly. And we see model 1 fits the training data this one should be the training data here. Model 1 fits the training data. Okay, perfectly. Means the error on the training data is very, very small, nearly 0. So this is our overfitting occurs now. And our intuition here is that you may say we don't want this model to fit our training data so well. Maybe we want to ask this model to fit our data a little bit more badly. So our intuition here is to prevent overfitting is that we don't want this model fit the training sample so well. Is that we do not want the model fits the training sample or training data so perfect. We don't want this model fits the data so perfect. Okay, so here we have these 2 training sample and testing sample, and maybe easily you may say that maybe this model is better. maybe this model is better, you may say. So you can see this model didn't fit the training data so well, and when you calculate the error of this model on the testing data, it will give you a much lower testing error. And thus, here I call this one model 2. And perhaps you will find the model 2 equation is something like this. Y hat 22 plus 1.5x. We say that this model 2 is better because it has low variance. It has a much lower testing error here. When you observe these two equations here, you may find that this is the slope. The slope is 2, and this one, the slope is 1.5. You may think that if we can decrease the value of the slope, maybe the model is better. Okay, this is our intuition here. And we say that model 2 is better. Why we say that it is better? Although it sacrificed the tuning error, means the model 2 will have higher bias. You remember what we have talked about, what is bias and what is variance. Higher bias, right? So we can see here model 2, this line is model 2. When you calculate the tuning error of the model 2, you will calculate this distance and you will calculate this distance. This is exactly not 0. You remember the tuning error of model 1 is 0. So here model 2 will have higher tuning error, but the benefit is that it has lower testing error, and thus lower variance, right? So we can compare the model 1 and model 2 here. The variance of model 1 is actually very high, and the variance of model 2 is obviously much lower than model 1 here. I hope you still remember what is variance here. Okay, this is this example. If you didn't get the idea, we can have another example. Suppose we have this example here. Also use this price of the house prediction example. We are all very familiar with this. Now, suppose we have this kind of tuning example here. We have a house 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 here. And then we have 6 houses again. And this time, and let's also draw our, this is the tuning example, tuning data. Okay, let's also draw our testing data here. Perhaps our testing data is like this. We have 5 testing data here. Testing data here. Okay, now we will not use this linear model. We will use maybe polynomial regression, and assume that we will choose m equals 4, that is degree. So this is the degree of the polynomial. we will choose 4-degree polynomial regression. And the model we choose is like this. Y hat equals to omega 0. This is the bias term. Omega 1 x plus omega 2 x squared plus omega 3 x raised to the power of 3 plus omega 4 x raised to the power of 4, because we choose 4-degree polynomial here. Okay, suppose we choose this model to fit this data. And after you fit the training data, you will find your model is something like this. Okay, this is the model. This is your first try. And I call it model 1. You can obviously see that model 1 is an overfitting model because it fits the training data so well such that it cannot predict our testing data. And let me write the model 1 here. Let's suppose model 1 you got the weights omega, so this is a vector. And you got the omega here, omega 1, omega 2, omega 3, omega 4 here. Okay, I need to clarify here that before here we will have a omega 0 term. And here from this on, we will not include this one to our omega vector. We will start with omega 1 here. And I will further explain this, but just keep this in mind. So there are actually two ways to represent the omega term, the weights term. You can sometimes include the omega 1 as the first entry, but sometimes you can also not put the omega 1 inside of this vector. You can put it as a separate bias term. Okay, let's suppose you find your model is like this. You got the weights. Okay, and your weights is something like this is the first weights. This is this first coefficient here, and the second coefficient, and the coefficient is something like this. Okay, and these numbers are only examples that I want to give to you, so don't be very strict on whether if this is right on this data. I just want to use these numbers to demonstrate this example. And let's also calculate the training error. Maybe the training error based on model 1 equals 0.1. If you want to calculate training error, you just calculate our prediction y hat, and you calculate the distance from each point. You can see that because our model 1 fits the data so well, so the training error is very low, very close to 0. And let's also calculate the testing error. How you can calculate testing error is you calculate the value, the value here, and you calculate this distance, you calculate this distance, and all the distance, and take the square and sum them up. Maybe you get 26.3. Okay, let's suppose you get something like this. Let's have another model. Because this is an overfitting model, we don't want overfitting. You may say that, I find a model like this. Let me draw it again. Okay, let's suppose this is the second model you get, model 1, also 4-degree polynomial, and this is the model, should be model 2. This is the model 2 you got. And also similarly, model 2, you find the weights vector is something like this. You can calculate the weights is these values, okay? And you also calculate the tuning error of this model 2. It's very easy. If you calculate the tuning error, you will calculate, so remember this green dots is our tuning data. And you calculate this distance, you calculate this distance, you calculate this distance. Of course, it's not 0, it's not 0.1 now, it's bigger than 0.1. Maybe it's 8.6. Let's also calculate the testing error. Okay, let's firstly find what is our testing data. This is our testing data. So you will then calculate this distance, this distance, this distance, this distance. You will find that these distances are much smaller than the distance to the model 1, right? So you will have smaller testing error. Maybe your testing error is this value, 6.5. And then you compare. You can see the model 1 is overfitted model. It's overfitting. It means it has very low tuning error here. But now, although our model 2 we get a higher tuning error, but the very good benefits we got is that we have a much lower testing error here. So this means this model 2 has a much lower variance here. And you can then observe how we achieve this, how we prevented overfitting. And then you should compare this weights term here. If you first compare these weights, this omega vector, you will find that all these values are much smaller than this one, right? If you want to compare, you can calculate the Euclidean distance of this vector, and you calculate the Euclidean distance of this vector. Of course, this one is much smaller. So here, our intuition here is that if we can decrease or minimize this weights vector, so maybe we can prevent overfitting here. This one is overfitted because you can see it has a very big weights here. This weights is bigger means that this model is very dependent on some feature, on this feature. We don't want this happen, so we want to minimize this weights vector. And we also want to minimize the tuning error. We want to do these two things at the same time. Okay, so this is what is called regularized linear regression. And I use two examples to help you understand this. Okay, and then we will have some formal equations here. Thus, and this is somehow very important. Our objective function becomes, so our optimization problem has been changed a little bit. We not only want to minimize the error, we also want to minimize the weights here to prevent overfitting. Omega star is the optimized weights, is this weights here. Omega star is equal to argmin omega arrow omega, and this is just a notation, so this means arrow. And you remember what is argmin here, equals argmin omega, and we will change our optimization problem to RSS omega. In several videos before, we only want to minimize this term, but now we will add another term, eta multiplied with R omega. And here we call this term, we'll give it a name as the regularization term. So this is the regularization term, and this is where regularized linear regression comes from. And please also pay attention that here omega is a vector, of course. This vector, before we said this vector is like this, omega 0, omega 1 goes to omega d here. And we say that omega 0 is the bias term. But here in regularization linear regression, we will not minimize this bias term. We will only minimize the weights that is connected with our features, because the bias term is not connected with the features. You can see here, this one, these weights, this 2 is minimized to 1.5, but this bias term is not minimized. It goes to maybe higher, from 20 to 22. And here we changed our notation a little bit. We just crossed out our omega 0 term, and please pay attention to that. Okay, this is the equation for the regularization linear regression problem. Of course, this is not finished. And let's see what is this 2. Well, this is maybe this one should be only R. So R omega, which is the regularization term. This term can be in different forms. Firstly, it can be in this form. We take the weights, we take the Euclidean distance of these weights. And okay, this 2 means we are taking the Euclidean distance, and we take the square of the Euclidean distance. Also L2 norm. And if the regularization term is in this form, we give it a name. We call it ridge regression. Also, you may say L2 regularization. These are 2 names of this term. And if it's not Euclidean distance, if it's Manhattan distance or L1 norm, okay, this is the L1 norm. So the L1 norm is you just take the absolute value of this entrance and you make a summation. So this is also sometimes called Manhattan distance. If this regularization term is the Manhattan distance, we give it a name, we call it Lasso regression or L1 regularization. Okay, these are just some names. Okay, you can see that these 2, this L1 regularization or L2 regularization, are very similar. We all want to minimize this term, and we just use different calculation method here. This one, we take the Euclidean distance. This one, we take the Manhattan distance. Yes, they are very similar, but I don't want to adjust the similarity. I want to adjust the difference here. Difference between ridge and the lasso regression problem. So the difference is that, so in lasso regression, some weights, that means some omega, some weights can be minimized to 0. Okay, it can take the value of 0. So when some weights, when some omega, for example this omega or this omega, is minimized to 0, so that means these two are gone, and it also means this term x raised to the power of 2, x raised to the power of 3 are useless, right? Because the weights with them are 0. So these features are gone. We don't care about these two features. Thus, it means that Lasso regression is used when, so Lasso regression will be used when you think some features are useless. You may think that in your data some features are useless, but you are still using them, but you know that some of them are useless. At this moment, you should use lasso regression. And this one, lasso regression, will cancel those useless features for you. On the other hand, in ridge regression, I will just say ridge regression is used when most features are useful. It also means that all those weights will not go to 0. It will only goes to very close to 0, 0.0001, but it will never take the 0. So these are two difference between the ridge regression and lasso regression. I think this is important to you. We also have a third one. That is a combination of this ridge regression and lasso regression. And L1 plus L2 regression L1 and L2 regularization. If we plus them together, we will have elastic net regularization. And this is a new name here. And in this regularization, the objective function is also changed a little bit. In this regression, we will both consider the ridge regression term and the lasso regression term. We will both consider this. And its objective function is argmin omega. This is the arrow. it will equal to, okay, firstly, we want to minimize our error. We also want to minimize the Euclidean distance of our weights vector. We give it a coefficient eta 1. We also have another one, eta 2, and multiply with the Manhattan distance of the weights vector here. Thus, we can see that the elastic net regularization is nothing but a combination of ridge regression and lasso regression, right? So it just combined those two. Okay, and I have covered what is this one, what is regularization term. It's nothing but these weights, these vector weights. And how about this eta here? This eta is also very important. And here, eta is called regularization coefficient. Which is a hyperparameter. Okay, we have a new term here. We have a new terminology here, hyperparameter. I will explain this later. And let's see what values eta should take. Let's see if eta here, if it is 0, this regularization term is gone. And what is left is just a normal linear regression. We want to just minimize the error, the residual sum of squares. So here, if this coefficient eta equals 0, it's the normal linear regression. Normal linear regression. And so what if we increase eta? As we increase eta to infinity, and let's see what will happen here. If we gradually increase this eta, so this term would goes to a very large value here. And our optimization algorithm will tell us that we want to minimize these two, but when we compare these two terms, the second term here would be dominant. So that means our optimization will mainly minimize the second term here. And what is the second term? The second term is the, the second term, we will only minimize the second term. The second term is the weights. So as we increase the value of eta, it means that we will no longer care about the training error, and the training error will go very large. But on the contrary, these weights will be dominantly minimized. So these weights will go to very small. So that means our model will become very simple here. Okay, so let me write here. So if eta goes to infinity, our model will be very simple. You may remember, if our model is very simple, what will happen? Maybe underfitting will happen. Because the model is simple, the weights here are all very small. Maybe in the end, the model will be something like just a straight line here. just a horizontal line. So this is a very simple model. When the eta is increased to very, very large. So this is what we call a hyperparameter here. And this hyperparameter needs to be tuned. Okay, and let me write something more. As the eta increases, the tuning error will increase. Because if this eta is large, our optimization will mainly minimize this second term and no longer care about the first term. So it means the tuning error will increase. But we have the testing error will decrease. And you can see in this example, so this example didn't demonstrate this point. So if we increase this eta, our optimization will simplify our model from an overfitting model. So it will give us a more generalized model here. So that means if we increase the eta from 0 to some value, the tuning error will be sacrificed. The tuning error will be increased, but we will have more generalized model. It means our testing error will decrease, and so overfitting will be mitigated. And if we further increase this eta, if we increase it to infinity, the overfitting problem may be changed to an underfitting problem. So we need to find the balance here. And finding this balance is called the hyperparameter tuning. And I think I can cover it in the next video. Okay, I think we can wrap it up here. In this video, we mainly talked about the 3 kinds of linear regression problems to prevent the overfitting. The first is ridge regression, the second is lasso regression, and the third is elastic net regularization. And we have also talked about hyperparameter. Although I didn't explain, I will explain it in detail in the next lecture. And we also talked about the different values of eta and what will happen if we take different values of eta here. Okay, I will stop here. Thank you for watching.